Welcome back to The Explainer. We're skipping the standard pleasantries today because we're looking at a massive, mind-bending question. Is Planet 9 actually a black hole? We're heading out to the darkest, coldest edges of our solar system, way past Neptune, to investigate a gravitational mystery that's literally baffled scientists for a decade. The leading theory has always been this massive, hidden ninth planet. But today, we're exploring a radical, frankly mind-blowing alternative that sounds like pure sci-fi, but is actually grounded in hard physics.
Okay, let's dive into this. For years, astronomers have been desperately hunting for a hidden world, famously dubbed Planet 9. But what if our search is turning up empty because we're looking for the completely wrong thing? What if the undiscovered ninth planet in our solar system isn't a planet at all? What if the culprit behind all these gravitational disturbances in our cosmic backyard isn't some giant ball of gas or ice, but actually a primordial relic from the very dawn of the universe? Today, we're framing this missing Planet 9 not as a planet, but as the prime suspect in a massive gravitational whodunit.
So let's look at the cosmic crime scene. Out in the Kuiper Belt, there's a population of icy bodies known as Extreme Trans-Neptunian Objects. Back in 2014, and then expanded on by Konstantin Baksin and Mike Brown in 2016, astronomers noticed something really strange. The elliptical orbits of these super-distant objects are oddly clustered together. They're all pointing in the exact same direction and tilted at similar angles. Now, the math shows there is only a tiny 0.007% probability of this alignment happening by pure chance. Battigan and Brown basically proved that an invisible gravitational force is out there in the dark pulling the strings.
By running some pretty extensive N-body simulations and looking at the orbital dynamics of these extreme objects, astronomers have built a physical profile of our suspect. And the math consistently points to a really massive object, something weighing anywhere from 5 to 10 times the mass of the Earth. Plus, it's incredibly far away. We're talking a highly stretched out orbit that keeps it roughly 300 to 800 astronomical units from the Sun. Just to put that into perspective, 1 AU is the distance from the Earth to the Sun. So at that extreme distance, a single orbit takes between 10 and 20,000 years to complete. Just wild to think about.
For a really long time, the prime suspect was a massive Neptune-like ice giant. But here's the thing, even at hundreds of AU away, a planet that big should emit at least some faint infrared heat or reflect a tiny bit of sunlight. But our sky surveys just keep coming up completely empty. Enter researchers Jakub Scholtz and James-Unwin in 2019 with a seriously incredible sci-fi plot twist. If this object is 5 to 10 Earth masses, its gravitational pull is exactly the same whether it's a giant planet or a primordial black hole. But here is the extreme contrast. A black hole of that exact mass would literally be roughly the size of a grapefruit, which of course makes it completely invisible to our telescopes.
So, the crucial point is understanding what a primordial black hole actually is. When we hear black hole, we almost always think of a massive dead star collapsing or, one of those supermassive monsters at the center of a galaxy. But primordial black holes are different. They're hypothesized to be ancient, tiny relics born from intense density fluctuations in the first fractions of a second just after the Big Bang. They can have the mass of an entire planet but be compressed into a tiny sphere you could literally hold in the palm of your hand. And just to be absolutely clear here, because it is so small and so incredibly far away, it poses absolutely no danger of swallowing the solar system. We are perfectly safe.
Now, you might be thinking this sounds like wild speculation, but it's actually grounded in real data. As Scholtz and Unwin point out, the probability of our solar system capturing a free-floating rogue planet versus capturing a primordial black hole is actually comparable. They back this up using observational data from the Optical Gravitational Lensing Experiment, or OGLE. OGLE actually detected an unexpected excess of ultra-short microlensing events pointing toward the galactic bulge. What that means is there seems to be a huge abundance of planet-mass compact objects, potentially these exact primordial black holes, just drifting through the Milky Way's halo. If the early solar system could have grabbed a free-floating planet, the math shows it had a very similar probability of snatching up one of these ancient drifting black holes instead.
Which brings us to the ultimate detective's dilemma. If our suspect really is a primordial black hole, it emits no light, it reflects no light, and it's the size of a piece of fruit sitting billions of miles away in the freezing dark. Conventional telescopes looking for the faint glow of a planet, they're never ever going to see it. So, how you catch a cosmic ghost? Well, to find it, we basically have to set up a cosmic sting operation. We need to stop looking for the object itself and start looking for how it interacts with its environment. Astrophysicist Amir Siraj and Avi Loeb came up with a brilliant method for tracking it down. They suggested that the black hole might periodically reveal itself by eating. Sounds crazy, right? But even though it's tiny, it still has immense gravity. As it orbits through the outer reaches of the solar system, it's moving through the Oort cloud, which is this vast icy shell of cometary debris, as well as the background interstellar medium. By interacting with all this material, the black hole would leave a sort of cosmic breadcrumb trail known as accretion flares.
Here's how this explosive process actually works. First, small icy comets just happen to wander a bit too close to the black hole's gravitational grip. At the same time, the black hole is sucking in background interstellar gas. That gas heats up tremendously as it falls in, and that intense heat actually melts and disrupts the approaching comet. Finally, as the comet gets violently shredded and consumed, it releases a brief, incredibly high-energy flare of optical or ultraviolet light. Siraj and Loeb calculated that these brief flashes of light could happen at least a few times a year. We just need a camera big enough and fast enough to catch them.
And as it turns out, humanity has basically just built the perfect trap. The brand new Vera C. Rubin Observatory down in Chile is equipped with a massive 8-meter mirror and literally the largest digital astronomical camera ever constructed. Its absolute superpower is its wide-field survey capability. It's designed to snap incredibly deep, detailed images of the entire visible sky every few days, which means it is perfectly equipped to catch these exact, short-lived accretion flares. If Planet 9 is actually a black hole snacking on tiny comets, the Vera Rubin Observatory definitely has the sensitivity to spot the flashes.
But what if we just don't want to wait around for it to eat a comet? And this brilliantly illustrates a much more proactive, radical alternative proposed by the renowned physicist Edward Witten. Instead of just waiting for a flare, he proposes we hunt the black hole down directly using a concept inspired by the Breakthrough Starshot initiative. This involves launching an entire fleet of highly advanced, incredibly tiny spacecraft out into the distant darkness.
This is quite literally a laser-launched sting operation. Step 1, we launch hundreds of tiny gram-scale probes into the predicted region of the sky, blasting them forward with super-powerful ground-based lasers. Step 2, they travel at roughly 0.1% of the speed of light for about a decade just to reach the outer solar system. Step 3, as they fly, they continuously transmit incredibly precise timing signals back to Earth. And finally, the trap springs. If one of these tiny probes flies close to the invisible black hole, the extreme gravity will warp space-time, causing a measurable microsecond delay in the probe's signal. We wouldn't just see the black hole, we would literally feel its gravity warp our clocks.
Now, to be rigorous here, we have to look at the active debate happening in the astronomical community right now, because not everyone buys the Planet 9 or the primordial black hole theories. For instance, some physicists point to modified Newtonian dynamics, or MOND. They argue that over millions of years, the gravitational field of the Milky Way galaxy itself naturally drags these outer icy bodies into the exact alignment we see today, no hidden mass required at all. Other astronomers argue this is simply observational bias. They suggest we're only seeing clustered orbits because of the specific times and places our telescopes have been pointing, so the whole anomaly might honestly just be an illusion of our own data collection.
And that leaves us right at the cutting-edge frontier of current astrophysics. Whether it's a massive, dark ice giant, an illusion created by galactic gravity, or an ancient, apple-sized black hole dating all the way back to the Big Bang, the outer solar system is clearly hiding some incredible secrets. With the Vera Rubin Observatory coming online and theoretical frameworks for laser-launched probes literally being drafted as we speak, we have to ask, will our generation be the one to finally map the edge of our solar system and discover a dark matter relic in our cosmic backyard? It's a fascinating detective story, and the best part is, the investigation is really just getting started.